worry too much about foreign object damage back in the turbine section. There's just too much in front of it to shield it. It is a potential problem. So you do have careful periodic inspections to look at things like foreign object damage or other problems in that section. Aqueous corrosion. All right, what I've been telling you about so far is oxidation. This is something we worry about at high temperature. In steels, aluminum alloys, chromium, the things that we use for structural materials, we don't ordinarily worry about oxidation at room temperature unless it's a disaster like mercury and aluminum or something of the sort. There is, however, a very common mechanism that can cause oxidation at room temperature, and that's known as corrosion, aqueous corrosion or rust. And that, of course, is a huge problem that costs us billions of dollars every year as things just rust away. What is it? What corrosion does is it creates a mechanism that permits oxidation to go on at room temperature. Now, what can that be? You already know that if we have this intact oxide film, that there's no way that oxidation is going to happen. So corrosion is a mechanism that, once the oxide film has been compromised, allows oxidation to occur without forming a protective film. And that's basically what the essence of corrosion is. It's just a mechanism to oxidize without forming a protective film. And the way that works is we use an electrochemical process that uses an electrochemical cell. What basically happens in this electrochemical cell, while we form an oxide, the electrochemical cell has the consequence that the metal ions are generated at one place, the oxygen ions are generated at another place, and the two get together somewhere in the middle. When we're oxidizing a metal with contact with the air, the oxygen comes in, the metal's already there, the oxide forms right where the oxygen hits the metal. In corrosion, the oxide forms someplace other than where the metal ions are formed. As a consequence, you never, ordinarily do not get a coherent oxide film, and the corrosion can therefore continue, and that's why corrosion is such a big problem at ordinary temperatures. Well, what happens? First of all, suppose we put a metal into some electrolyte, some solution that might contain the ions of the metal. Why doesn't it dissolve? Why don't metals dissolve in water and such things? The reason is really pretty simple. Suppose I have zinc here, as an example. Zinc, if I put zinc in contact with a solution, water, I will begin to get some dissolution of the zinc. Into the water will go zinc ions like this. But the zinc ions leave electrons behind. So after a short period of time, I will build up an electric charge here in the zinc, another electric charge out here in the electrolyte. Separating the electrons and the ions becomes increasingly difficult because it's fighting this electric charge. And as a consequence, the process stops. So you put zinc or some other metal into water, you will get some dissolution, but very little, and the process will immediately stop. This is not a method for attack. Suppose, however, that we now complete that. We give the electrons someplace to go. We create what's called a galvanic cell. Suppose I have here a zinc electrode, just like I had before, in contact with some electrolyte, in this case sulfate. And suppose I take a wire and I attach that zinc electrode to copper. Now, zinc and copper have different potentials. So an electrical potential will spontaneously develop between the zinc and the copper. Basically, that happens because of the difference in Fermi level between the two materials. They are the Fermi level, the energy of the most energetic electrons in zinc is higher than in copper. So electrons will tend to run from the zinc to the copper so as to equalize the Fermi level. Now, if there were no water here, that process itself would go on just a little bit and then it would stop, because you get an accumulation of charge over here in the copper, and that would fight the addition of more electrons, and your current would stop. But now let's suppose we have them in contact with an electrode. Zinc ionizes, goes into solution, releases two electrons. The electrons run over here to the copper. If there's copper in the solution, then the electrons in the copper can now combine with the copper electron to produce played out metallic copper, and that consumes the electrons. So now we have a circuit. Electrons are flowing from zinc to copper, ions are flowing through the solution, and the whole thing is an electrical balance. So the potential difference between the zinc and the copper never goes away, and this can just keep going and going and going until all the zinc or all the copper is consumed. And that's what happens in a galvanic cell. Now notice what's going on here. In this case, the liberation of zinc ions is corroding the zinc. The other thing that's happening is the plating of copper on this side. This, by the way, is a good example of a cell you might use to plate copper on places you want to plate copper. The zinc is going into solution. The copper is plating out over here. There's absolutely nothing to seal off this zinc surface. So it just keeps corroding and corroding and corroding until it's finally gone. And that's the essence of corrosion, is this electrochemical cell that allows ions to be exchanged, electrons to be exchanged in a circuit that just doesn't go away until all the material is consumed. This is just an illustration of where that potential is coming from. If this is one metal and this is another, here's the Fermi level. The difference between the Fermi level and free space is what's called the work function phi. That's a potential. And you see that the lower the Fermi level, the higher that potential is. And electrons will flow from the material that has a lower work function to the material that has a higher work function, and here's the potential difference between them. And that's basically what's going on. It reflects the difference between the Fermi level. It's also slightly affected by the nature of the solution. The easier it is to ionize the stuff that's in here. Some ions, for example, will hydrolyze with water. They get in the solution, they attract water molecules, and that lowers their free energy. So if this material just happens to like water, then that will effectively raise its work function and make it more susceptible to corrosion. So there are other things that happen here. Half-cell reactions, we can look at the work function, essentially, the potential involved in various reactions. Gold going to gold plus 3 electrons, very, very high voltage required. Copper, positive voltage. Iron, negative voltage. Chromium, zinc, and so on. If I put these two together and make the reaction, N1 plus M2 goes to N1 plus M2 plus, that is the ionized, goes to M1 plus M2, then the potential is just the difference of the work functions. To get gold to exchange with iron, to ionize, would require a positive potential of almost 2 volts. So there's very little desire to do that. If, on the other hand, I take metallic iron and ionize gold, if I could do it, then there is a very strong negative potential to get that iron to oxidize, so gold would cause a very rapid corrosion of iron, which gets to the dumbest idea I ever heard, one of the dumbest in engineering. There was, I don't know if it's true anymore or not, it used to be every Christmas, the American Express Company would come out with a Christmas catalog. And at the back end of the Christmas catalog, they would offer some very exotic thing at some enormous price. I don't know if anybody ever bought these things or not. But I remember one year, gosh, I think it was back in the late 70s, they came out, and on the back, there was a kind of a dumb idea of a car that came out at that time. When I first came to Berkeley, I was coming out of industry. I made some money in the stock market, and I said, I got to buy myself a sports car because I paid a huge pay cut to go to campus, and so I'll never be able to afford one again. So I bought a Lotus Europa, a little plastic car, mid-engine car, fabulous car, drove it across the country. I can tell other stories about that, the quality of British craftsmanship. It was a lot of fun to drive. Someone named DeLorean came out of General Motors. and decided he got a huge amount of money from the British government to set up a car company in Ireland. And what he did was he took the Lotus Europa, basically, same engine, everything, only he replaced the plastic body, which made it very light and maneuverable, with a stainless steel body. So you had to move up the engine, the whole thing became very heavy. It never was very practical or much fun, but it looked great. So he was putting these things out in Ireland. And that particular year, to compound idiocies, the American Express thing of the year for $100,000, which in those days was an enormous amount of money, you could buy a gold-plated DeLorean, the stainless steel plated with gold. I looked at that, I said, somebody has got to be nuts. Take that out. Suppose you plate it with gold. You're driving around. The gold coating somehow gets scratched. It can't be too thick. It's gold after all. It gets scratched. What have I got? I've got a huge amount of gold concentrating on a little bit of stainless steel, and I'm going to get corrosion like you can't believe. The only thing that's going to save it is that the potential may be so high that it creates enough oxide to passivate seal the surface off and stop it. So I've always wondered what happened to those cars. And somebody, E45 a couple years ago, told me, I haven't verified this, that there's a car museum up in Reno that apparently has one of these things. Reno's a fairly dry area, the desert's still there, but you can't see it. It's genuinely there out here. The galvanic series. If we put two metals together, one is going to become the anode and be corroded, the other is going to become the cathode in the galvanic cell and will be protected. To understand which is which, it really gets into both the work function of the material, alloying affects things, affects the free energy of the material, the nature of the environment affects things, and are we talking about salt water, fresh water, what's the composition of the salt water? There are a number of things that will affect the potency of a corrosion couple. But for general purposes, we have what's called a galvanic series and seawater. Imagine that this is all one column instead of being broken up into two here. On the bottom of the column are things that are cathodic, that is, they are not corroded. On the top of the column are things that are anodic, they corrode very easily. If I have two metals that are in contact to create what's called a galvanic cell, the one that is lower in the galvanic series will corrode the one that is higher in the galvanic series. I should say in this galvanic series, because a lot of people do it upside down. But anyway, in this galvanic series, the lower one will corrode the higher one. So wrought iron will corrode aluminum copper alloys. Gold will corrode anything. Stainless steels will passivated, that means they've already got good oxide coating on them, will also corrode most things. Given two dissimilar metals in contact, the one that's lower in the series will corrode the one that's higher in the series. Anytime, from the point of view of basic engineering, anytime you ever have dissimilar metals in contact, one is going to corrode the other. It's just a question of which way. One of the first rules of life is if you're ever going to put two dissimilar metals together, you've got to protect them somehow, or one is going to corrode the other. People constantly forget that, but it's a law of nature. Okay, so one way we get corrosion is this galvanic cell. The anode ionizes. The cathode can have some reaction, but it's not going to corrode. The anode is going to be the one that corrodes because the electrons flow from the anode to the cathode. And I can identify the anode in galvanic corrosion from this galvanic series. Anytime I have two dissimilar metals in contact, that's called a galvanic couple, and there will be corrosion unless I do something clever to stop it. However, that's not the only way that I can get corrosion. The other way I can get corrosion is what's called a concentration cell. Suppose that I have here an electrochemical cell in which I have both sides of the cell I have zinc electrodes. Let them be in contact with solutions, and let's assume I have a membrane in here which is impermeable to zinc ions, so I can have different zinc concentrations. And let's say on one side of this barrier, I have a low concentration of zinc, and on the other I have a high concentration of zinc. Well, you know perfectly well what's going to happen. Over here, the chemical potential of the zinc is going to be higher because it's a high concentration. So if there is a possible reaction which will equalize the concentration of zinc, it will happen. So what's going to happen, and you can actually calculate the potential difference, it just looks like this. What's going to happen, just from basic thermodynamics, is that the zinc in contact with the low zinc solution will be corroded by the zinc in contact with the high zinc solution. So this zinc will corrode, on this side zinc will plate out. And that process will continue until the zinc concentration on the two sides of the membrane is equilibrated. That's what's called a concentration cell. And that's a major source of corrosion in the real world. Okay, let's talk about iron, because that's the main thing that corrodes that we have to worry about. In iron, generally, both the anode and the cathode are iron. When you see a piece of iron rusting like a knife in your kitchen, or something sitting out here, or an iron pole sticking out of the bay, it's all iron. So whence does the galvanic cell come from? Well, the galvanic cell can come from a number of sources. There can be regions of the iron, because of difference in fabrication or difference in microstructure, have different chemical potential, and therefore one becomes the anode and one the cathode. There can be concentration cells of various kinds in the iron. I'll talk about exactly what that is in a moment. But let's just imagine that we have two pieces of iron here. One becomes the anode, one the cathode. The anode releases iron ions. The cathode does what? Well, it turns out there are various reactions that can happen out here at the cathode. Very few of those reactions involve iron itself. Rather, they involve things that go on in the solution, in the water. A normal cathodic reaction involves oxygen. 2 electrons plus 1 half O2 plus H2O go to 2 hydroxyl ions. In acidic solution, we may evolve hydrogen. You may have seen that at one time or another. In very strong potentials, we may break down the water itself to produce hydroxyl ions. These normal reactions, in particular this, top one, which is a normal reaction in the corrosion of iron, produces hydroxyl ions. So what happens? At the anode, we're producing iron ions. At the cathode, we're producing hydroxyl ions. They get together somewhere in the middle, and they interact together to form rust. That rust is not located precisely on the surface. So unless the cell is just properly configured, that rust is not going to form a coherent film. As a consequence, we're going to get kind of a rust, spongy thing, the rust you're accustomed to seeing, and it's just going to grow and grow and grow until the iron is finally consumed. And that is the normal reaction in rust. The anodic reaction, iron is being oxidized, sometimes to Fe2+, sometimes to Fe3+, depending on the conditions. On the cathode side, normally we consume oxygen and produce hydroxide. And that's the cathode reaction. And the net result is rust. Well, so why are we getting corrosion? Well, galvanic couples we already talked about when they're dissimilar metals. If we have a single metal, such as iron, very often microstructural heterogeneities, a more stable grain or region, will lead to one grain becoming the cathode and another the anode. There may be a local increase in free energy due to mechanical deformation or defects, due to chemical heterogeneity, due to phase or microstructural differences. So that there will be regions of the surface that become cathode, regions that become anode, and as a consequence, corrosion will occur. This always happens in ordinary metals. There just isn't a metal out there that we use for structures that is so uniform in its surface that there will not be some regions that are more reactive than another. So if we take any of the common metals that you're familiar with and put them in contact with an electrolyte like rainwater, there will develop a galvanic cell on that surface and corrosion will commence. It's always there. The other thing that happens quite commonly, getting the time here, is oxygen concentration cells. If you have ever seen, if you go down to the bay, just off of 80, where the bay is kind of shallow just before you get to the bridge, for reasons that I do not know, there are a number of iron poles sticking out of the water down there. If you were to go look at those iron poles, you would find corrosion. And the interesting thing you would notice about that corrosion is it's not right at the waterline. The corrosion is always maximum a bit below the waterline. The waterline is up here, the corrosion is worse down there. Why is that? The reason is that the ordinary reaction consumes oxygen. If you go down to the bay, the oxygen is coming in from the atmosphere. So the layer of water right next to the atmosphere is relatively rich in oxygen. Since it's rich in oxygen, that's the cathode in the reaction. Slightly below that, where the oxygen is leaner, since it's lean in oxygen, that becomes the anode in the reaction. So the oxygen-rich material corrodes the oxygen-poor material. And that's why the corrosion almost always occurs just a bit below the surface. And that is a source of a huge problem. I don't know if you've ever seen a tank, for example, that's been corroded through. I'll finish on this point. But almost always, the corrosion through that causes the leakage in the tank is not general. Very local. There'll be a little pit at the bottom of the pit. You'll see a pinhole penetrating the surface, and that's where the corrosion will have penetrated through. Why does that happen? Let's suppose we have water here in contact with the metal, and let's suppose we have a pit in the surface. I've idealized it here. Out here to the top of the pit, we're close to the free water. So oxygen is high. So this is the cathode. Down here at the bottom of the pit, we have a dearth of oxygen. So down here is the anode. The net result is that when we have a pit in the surface, the corrosion is such that the pit tends to deepen itself. Corrosion basically just tunnels through the material. And that's why when you do see corroded surfaces, you will very often see pinhole penetrations, pits, roughnesses in the surface. It's because of this reason. Well, the next thing I got to tell you about is how do we stop corrosion. And I'll do that. That's going to be quite a while because we have the exam on Wednesday, open book in this room. We will have, you will be off on Friday because we cancel class on Friday, and then you have your vacation. So you won't have a regular lecture until 2 weeks from today, I guess, and then we'll finish talking about corrosion. So I will see you on Wednesday for another purpose.